So first off, thanks for coming everyone to my presentation today, and also for B-Sides, thank you for the opportunity to talk on the project, and hopefully there'll be something here that's interesting for everyone. Yeah, it's been a bit of a labor of love so far, and yeah, so this is my secure notebook, and feel free to come and inspect it closely at the end if you like. And let's get into a little bit about what it is. Yeah, if I was in America, I guess I would say that I'm trying to build the most secure notebook-taking device that exists. But because we're not in America, we're in the UK, this is my lovely little side project, which I hope you'll find interesting. Yeah, so a bit of the secret history of the world, really, like how I stumbled upon this project. Mostly because I had a large interest in secrets. More specifically, is there a perfect secret system existing? And the Frank Miller reference, the Sin City reference, is a little bit irrelevant, but there is a Civil War era banker and crypto nerd who invented something called the one-time pad. And the one-time pad is a pretty close to perfect secret system. It was later patented at Bell Labs, which happens to be the same place that maybe some of you all know, Claude Shannon worked. He's the modern father of information theory. And these days, it's been digitalized and is used in diplomatic channels and by the military, mostly. And this is the original. It's got this nice property that it's information theoretically perfectly secure. However, the caveat is that the passcode for your device has to be as complicated, as long as the secret itself. So it's hard to remember the passcode. And as like the name says, it's a one-time pad, so it only works once. So it's not super ready for user use, really, except in these channels. So I kind of moved on from this. So anyway, a bit of an intro to me. I was trained as a mathematician at university. I then spent some time with Wolfram in their data engineering team, moved to ARM, and their GPU team, worked there for a while. Spent a while freelancing for startups and building their MVPs. Then I got my security clearance at a company and worked on a black box on radio frequency stuff. Then I was inducted into the madness of fintech in Canary Wharf for a little while, and I'm now here talking to you guys. So the problem context that we're dealing with today, it's quite specific, so bear with me for a sec. I am a little bit new to the security space, but I have noticed a trend, and which is that we, as a population, as a people, we prefer convenience than security, and there are trade-offs that have been made because of this. And the trade-offs, technologically, are on the CPU. They're on something called cache inside the CPU. There's really fast access memory. Disclaimer about the project: I'm not solving for some threats that do exist out there. So there's side channel threats. We're not solving for a drone spying over your shoulder and recording your keystrokes. We're not solving for the bug that's been planted in your office and that is giving telemetry to remote AI models and reconstructing passcodes based on the sound of your keystrokes. And we're definitely not solving for hardware level, like manufacturer level implants in chips. And so this is a graphic that I took from a really good video that I recommend everybody go watch, actually, if you're interested in this kind of stuff, called Mod Chips of the State, by a guy called Trammell Hudson, and it's a CCC talk. What you're seeing here is like a massively electron microscope zooming in on a chip, and there is that's not meant to be there. That's an ARM Cortex CPU embedded inside of another CPU. Don't know what that's doing, but not something good. Yeah. Okay. So a bit more into the technical side of the problem. So these bugs that have occurred recently. First one was spotted in 2018. by some Google developers. And more recently, there's one that's been spotted in 2021 called Pac-Man. And what they do is so chip architects to solve for this problem at the time of applications not going fast enough, they introduce cache into the architecture of the CPU. And that enables something called branch prediction. Branch prediction is you can think about it as if when a program is running on your computer, the CPU will try to execute lots of different potential outcomes of the branches all at once. But to do this, it kind of has to remember in case it makes a mistake and has to go back to a state that was known to be true. So cache was introduced to do this. You could use RAM, but it'd be hundreds of times slower because it's further away physically. And so what do attackers do with this? They perform a side channel attack. They fill the cache up with data, and they measure the time taken for random operations, like specific operations, to be done on the cache, and can infer private data from that methodology. When I talk to friends and family about this problem, this is how I imagine they see me, pretty much. But I think there is a real future where Apple or any other of these large companies who are manufacturing phones have put a little AI device in your phone. And this AI is trained on every single bug that exists on the internet. And who knows, maybe when you get your device, you give it access to your phone. Suddenly there's all these bugs that can be exploited at large. Because the reality is that at the moment, this specific problem probably is only affecting people of high value, and systems are very high value. I think at the moment it's not a big concern for most people, but in the future, maybe yes. So with all that in mind, I got to building stuff because that's what I like to do, and landed on a philosophy for designing this thing. I wanted a minimalist execution environment running on bare metal. What that means, no operating system, because that has a lot of unnecessary things in it. Each of the components that I'm building with are modular, and both the software and the hardware, so that makes them easily upgradable. Some technology that I decided to go against. So this is CPLD up here. It's very nice. It solves most of my criteria, but actually it contains embedded persistent memory, and that fails the minimalism kind of criteria. Don't need embedded persistent memory for this project. I'll explain a bit more about that and why later. And this is a kind of a classic microcontroller. They're cheap as chips, but they're programmed with C, and there are a lot of C vulnerabilities out there. So landed on the FPGA as a technology to build on. It stands for Field Programmable Gate Array. And why does this allow for a solution to the speculative execution problem? You're designing electronics with it. So you can design your program to execute purely sequential operations. So no branch prediction. And then memory can be implemented and re-implemented in any way we choose. So it doesn't have to be a heap or a stack. It could be whatever you want. However, it is hard to design these on this tech for an end user, and they are more expensive than microcontrollers. So overall, very nice, I think. And we're going to go with that one. Designing with FPGAs, you are building on electronics, and so especially when you're communicating with devices, peripherals around the FPGA, you end up having to deal with waveforms a lot. So this is a waveform that you might see, and it implements something called the SPI protocol. There was actually a workshop on this earlier that you might have been at, some people, but what it comes down to is to build your solution with a home lab, for instance. And as you can see here, there's a logic analyzer and a probe that's attached to one of the little arms of the chips, and you can record the data that your program, that your software makes, that your design outputs using this tech. And there's an FPGA there that creates signals. Could be a CPU if you wanted, but not for this project. There's some 2-pin buttons and OLED display as well. So the lab has evolved. Originally, this was V1, I guess, and it was very cable salidy. V0 was even more cable salidy, but the iterative thing hopefully will end up with a PCB eventually. So the project has a lot of growth potential. Like, if you want to learn about material science, it's really possible to do that with this technology, FPGAs, because you kind of have to think in terms of the material science of it. There's a lot of stuff that I will never know, and usually this is the meme that I come back to when I'm thinking about computers. So the design, the blueprints, it was a top-down approach. This is the top-down approach. And there's 4 main components, as you can see on the board. There's the inputs, there's the display, there's the FPGA, and the flash. That's the memory, persistent memory. And so you can see here is a slightly more in-depth design for the protocol itself, which is, included all the drivers and the opcodes to get things to work properly. So how do we write FPGA software? FPGA software, you're actually creating HDL. So you use software to describe hardware, you compile the software into a bit stream and upload it to the FPGA, and it will essentially run like a program, I guess. I'm a bit outside the scope of this talk. If you want to hear more about this, I recommend watching Clifford Wolf's CCC talks. They're really good. So, an FPGA, one more thing about it is it's best working when every submodule and every module in it is working as a finite state machine. Again, something a bit outside the scope of this talk, but in practice, it's good to remember that every time your hardware design reads a clock cycle, a round of logic is executed. Doing it this way is extremely fast at the nanosecond timescale, actually. So you can't really do much better, if I'm honest. So yeah, that was my talk. Thanks for coming and your time. And if you're interested in the project or want to keep updated, there's some details here. QR code, I'm realizing after today, probably not the best thing to have shared at this conference. People don't seem to trust them. So, give me an email.
Thanks, Kai.